Alright, now that we know how to do Laplace transforms, next up is inverse Laplace transforms. So, f of s represents the Laplace transform of a function f of t, right? We talked about this already. This is the Laplace transform for this. So, if we're trying to do the inverse Laplace transform, it's going backwards. We'll start with the Laplace transform and we have to get back to the original function. So, if we know that the Laplace transform of t is 1 over s squared, then the inverse Laplace transform of 1 over s squared gets me back to t. Also, the Laplace transform of e to the negative 3t is 1 over s plus 3. So the inverse Laplace transform of 1 over s plus 3 gets me back to e to the negative 3t. So this is the notation for the inverse Laplace transform using this inverse notation that you've seen all throughout your math careers. So now we have to look at what properties that has. Well, guess what? Since the Laplace transform has a linearity property, the inverse Laplace transform has the exact same linearity property, which means constant multiple rule and sum and difference rule. So we can split apart the inverse Laplace transform doing this. All right, so we had certain Laplace transforms. One was for 1, so the inverse Laplace transform of 1 over s gets me back to 1. We talked about powers, so t to a power. So the inverse Laplace transform of s over n factorial over s to the n plus 1 is t to the n, sine, cosine, exponentials. It's just reversing everything we've done before. These are the most common ones, so these are ones you should know at this point. All right, so let's look at these two examples. So 1 over s to the fifth, inverse Laplace transform of 1 over s to the fifth. Well, it should be a power, but if you notice, we're missing the n factorial over the top. In this case, we're missing the 4 factorial. If this had a 4 factorial here, then we'd be all ready to go for t to the fourth. But it doesn't. So what are we going to do? Well, remember, we have that linearity property, right? So what we can do here is we could say, let's multiply by 4 factorial over 4 factorial for this inverse Laplace transform of 1 over s to the fifth. We could pull constant multiples out, but we can also put constant multiples in. So I'll put this 4 factorial in here. So I have 1 over 4 factorial times the inverse Laplace transform of now 4 factorial over s to the fifth. So then I'm going to get 1 over 4 factorial t to the fourth. So there's my answer. Pretty simple. How about this one? Inverse Laplace transform of 1 over s squared plus 7. 7, 7, 7. All right. So you should right away be thinking sine or cosine. Now the problem is cosine, you need an extra s in the numerator, which is not a constant multiple. So that's not going to work out as well as the sine one, where you have a k in the numerator, k being a constant. So in this case, we're essentially missing square root of 7 right here. If we had a square root of 7, then this would be in the form for the sine. Well, same thing we did in the last one. If I multiply by square root of 7 over square root of 7, I got my inverse Laplace of 1 over s squared plus 7. So my answer is going to end up being 1 over square root of 7 sine of square root of 7t. Move this one in. We have everything we need for sine kt, k being square root of 7. There's my answer. So if you have your Laplace transform memorized, you should be able to then easily do the inverse Laplace transforms. It's not going to be that simple all the time, but we're going to base everything off of those. All right, think about this one. This doesn't look like either sine or cosine. It's kind of a mixture of both. but use a lot of the things that we've used throughout calc to get through this one. One thing we've always talked about is splitting apart fractions. So if I look at this and I say, how about the inverse Laplace transform of negative 2s over s squared plus 4 plus 6 over s squared plus 4? Split that numerator apart. This one has more of a form for cosine. This one has more of a form from sine. We got to mess around with these numerators a little bit more, but we got what we need generally. So we could say, pull the negative 2 out of this one. Inverse Laplace transform of s over s squared plus 4. Plus, I need a 2 up here, not a 6, so I could pull the 3 out, leave the 2 in, and I'm ready to go for sine. So here we go. This one right here is cosine. So it's going to be negative 2 cosine of 2t plus 3 sine of 2t. So sometimes you got to do a little bit of manipulation with it, but eventually if you can get it back to one of our basic functions that we do Laplace transforms for, you'll be able to handle this. So again, this shouldn't be too bad. All right, then we have this one. Now this one would require us to split apart the denominator more than the numerator. Well, the splitting apart a denominator of a fraction takes a lot more work than the numerator. The way we do it primarily is partial fraction decomposition. I know you all love partial fraction decomposition, so this should be lots and lots of fun. So listen, if this thing was, say, I don't know, 1 over s minus 1, or 1 over s plus 2, or 1 over s plus 4, and we had to do the inverse Laplace transform of one of these, that shouldn't be a big deal, because this would be an exponential, or an exponential, or an exponential. So if we're going to try and split this denominator apart here, again, partial fraction decomposition is what's going to be needed. So let's do some partial fraction decomposition. S minus 1, s plus 2, s plus 4. So to split this apart, we'd split apart the denominator, which are these separate factors. They're all linear factors, which is nice. S plus 2, s plus 4. Now it's just a matter of figuring out what the numerators are. Since the denominator is a linear, the numerator would be a constant, so a1, a2, a3. Alright, so then we mess around with this equation. It's easier if we can get rid of all these fractions, so we multiply everything through by that common denominator. So this side becomes 1. Here we get a1 times s plus 2 times s plus 4. Here we get a2 times s minus 1 times s plus 4. And here we're going to get a3 times s minus 1 times s plus 2. And since these are all linear factors, the easiest way to get through this is to say, okay, let's let s be one of the zeros for one of these factors. So let's let s equal 1. How about s equals negative 2? And how about s equals negative 4? So when s equals 1, the left side is still just 1. The right side, anything that has an s minus 1 in it becomes 0. So this one is 0 and this one is 0, leaving me simply with a1 times 3 times 5. So a1 equals 1/15. If I do negative 2, again 1 on the left side, anything with an s plus 2 in it, which is here and here, that zeroes out. So that leaves me with a sub 2 times negative 3 times 2. So that'll give me a sub 2 to be negative 1/6. And finally, s equals negative 4 would be 1 equals a sub 3 times negative 5 times negative 2. So a sub 3 equals 1/10. So now that we know what these numerators are, we should do the inverse Laplace transform of that sum. So it would be the inverse Laplace transform of 1/15 over s minus 1 plus negative 1/6 over s plus 2 plus 1/10 over s plus 4. Remember, these are just all constant multiples anyway, so when I go to do the Laplace transform of each one of these, they can come out. So I'll really have 1/15 times the inverse Laplace transform of s minus 1 over s minus 1 plus negative 1/6 times the inverse Laplace transform of 1 over s plus 2 plus 1/10 times the inverse Laplace transform of 1 over s plus 4. So what does that give me? Well, it's going to give me 1/15, and this is going to be an exponential, specifically e to the 1t minus 1/6 times this one will be e to the negative 2t. That's for this one. And then we got a 1/10 e to the negative 4t. Okay? Because remember, it's always 1 over s minus k, k being the e to the k, t with our Laplace transform. Okay? So this is your inverse Laplace transform for this function. Little partial fractions needed, but when you add a split apart in the denominator, that's what you got to make sure you do. Okay, here's another one. Same deal. Thinking about this. It doesn't initially look like a fairly simple one. We could split apart the numerator, but that's not going to do anything. S over this plus 1 over this doesn't really help us with the inverse Laplace transform. Thinking about splitting apart the denominator may be a little bit more useful. So let's look at partial fraction decomposition. S squared times s plus 2 cubed. So let's think about this. So I could have s as a denominator, s squared as a denominator, s plus 2 as a denominator, s plus 2 squared, and s plus 2 cubed. Now, it's a lot. Okay, remember whenever you have a denominator raised to a power, you always have to start with it to the first power and work your way up to whatever the highest power is. The thing though is that the factor s and s plus 2, those are all linear factors, so the numerator in each case would just be a constant. So a1, a2, a3, a4, a5. Now, consider these problems. Before we go through and do all the work we're going to do, if I'm going to have to take the inverse Laplace transform of each one of these, will I be able to figure out what the answer is? Is this something that I can get done fairly easily? Well, this one, yeah, okay. Constant over s, we should be able to handle that. That's just really going to be a constant times 1. S squared should be t to the first. We're going to be able to do that one. This s plus 2, we should be able to do an exponential function to handle that. Now these two may be a little bit trickier, but think about it. These are going to be using that translation function, that first translation theorem. So, you know, if it was just s squared, it will be a lot like this, but it's s plus 2 squared. So this is where we're going to have to do that exponential e to the at times f of t. Remember that Laplace transform using the translation theorem, where you do f of s minus a. So I'm doing s plus 2, so a would be negative 2. And I'm going to be plugging that into the Laplace transform for f of t, basically. So this is going to be a power function times an exponential. This is going to be a power function times an exponential. So looking at this, regardless of what a1, a2, a3, a4, a5 are, we should be able to do the inverse Laplace transforms once we figure out what those constants are. The thing that's going to take a long time is figuring out what those constants are. This computation is not going to be something that gets done quickly. But once we do it, we should be able to figure out the inverse Laplace transforms with relative ease. Alright, so what are we going to do here? We're going to simplify this by getting rid of all this fraction business. So we got s plus 1 on the one side. We're going to have a1 times s plus 2 cubed. We're going to have a2 times s plus 2 cubed. We're going to have a3 times s squared times s plus 2 squared. We're going to have a4 times s squared times s plus 2 and a5 times s plus s squared, I should say. Let's get rid of here s squared. So we'll let s equal 0. We'll let s equal -2, and then I'll get rid of some of this. When s equals 0, this side becomes 1. This, they'll all be 0, so I'll get a2 times 2 cubed. So it's 8, so a2 equals 1/8. So we got one of them down. If I let s equal -2, this side becomes -1. All these s plus 2's are going to be 0, so I'll get a sub 5 times -2 squared, so 4. So a5 equals -1/4, but then we're kind of exhausted at this point with that. We still have to figure out a1, 3, and 4. We could do a system of equations and try and use linear algebra, or other option is to just multiply everything out and set up a system that way. I like doing it, multiplying the right side out completely and then doing what I call the equal parts method. So if I was to start multiplying this out, first off, s plus 2 cubed is s cubed plus 6s plus 12s, sorry, s squared, plus 12s plus 8. And then the a1s goes into that. So I'm going to get a1s to the 4th plus 6a1s cubed plus 12a1s squared plus 8a1s. Then a2 is going to multiply into here. What I'm going to do is, or a2, sorry, is going to multiply into here. What I'm going to do is I'm going to start stacking it under what I already have to make it easier. Plus, I don't have enough space this way anyway. So I get a2s cubed plus 3a2s squared plus 3a2s plus 8 a2. I gotta switch some of this. I messed that up. Let's try that again. Again, s plus 2 cubed is right here. So I'm really multiplying a sub 2 times that. So let's try that again. A sub 2 s cubed plus 6a2s squared plus 12a2s plus 8. 8a2. Okay. And this is going to multiply out, and this is going to multiply out, this is going to multiply out. So s plus 2 squared is s squared plus 4s plus 4. So that's going to give me a a3s fourth, a3s to the 4th, then a 4a3s cubed, then a 4a3s squared. We're almost there. Okay, this one multiplied out is going to give me a a4s cubed. Then we're going to get a 2a4s squared. And the last one's going to give me a5s squared. Okay. So now that this is all grouped vertically, I can start putting all these together, and that'll help me find what I'm looking for. Remember, I'm looking for a 1, 3, and 4. So let's look at this one right here. This tells me that a1 plus a3 s to the fourth would happen when I put my s to the fourths together. There is no s to the fourth on the other side. So if this side has an s to the fourth, but this side doesn't, the only way they're equal is if this coefficient equals 0. So I know that a1 and a3 basically have to add together to give me 0. I don't know what either of those is yet, so I'm working towards that. We'll get there. Let's look at some of these other ones. Here, this is a2. That's the only constant I have. The constant on this side is 1, so I know that this has to equal 1. Well, if that equals 1, that's going to tell me that a2 equals 1/8. I already know that, but that verifies what I found over here. All right, let's take a look at this one. This tells me that 8a1 plus 12a2 has to be the coefficient in front of the s. The coefficient in front of the s over here is a 1. So that means this has to equal 1. Now here we're going that a2 is 1/8, right? So this tells me that 8a1 plus 12 times an eighth has to equal 1. Well, 8a1 plus 12/8 has to equal 1. So the only way that's possible, right, is if you move this over to the other side and then divide by 8, you can figure out that a1 is going to equal, what's that going to be, negative, so we'll get negative 1/16 for a1. Now knowing that, let's come back over to this one. If a1 is negative 1/16, that also tells me that a3 has to be positive 1/16 for me to get 0. So now I just got two things out of here. So I got one more to go. I got to figure out a4. Where am I going to figure out a4 from? Well, this is probably the best place to get a4. Okay, so if we're going to get a4, we know a1, we know a2, we know a3, and the sum of all of these put together is the coefficient in front of s cubed. There's not an s cubed over here, so that sum has to equal 0. So that'll help us figure out what a sub 4 is. So 6a1, which would be 6 times negative 1/16, would be negative 6/16, plus a2, which is 1/8, plus 4a3, which is 4/16, plus a4 has to equal 0. So doing all that computation, probably the best thing to do is say 1/8 is really 2/16. So this is basically going to tell me that this whole thing here is really 0 when you look at it. So if that's 0, then this tells me a4 has to equal 0. So now I got all my coefficients. Okay, so here are the fractions that we got to take the inverse Laplace transform of, being that we did a1, a2, a3, remember a4 was 0, and a5. So the first couple should be really easy. If I do the inverse Laplace transform of this, I should get negative 1/16 times 1. The next one should be 1/8 times t. The next one should be 1/16 e to the negative 2t. And then there's just a matter of getting this one. Okay? Again, remember, we're going to do the translation theorem. If we know that the Laplace transform of t squared is 2 over s cubed, and I'm trying to do the inverse Laplace transform of negative 1/4 over s plus 3 cubed. Okay? We're going to look at another Laplace transform, and that would be the Laplace transform of e to the negative 3t times t squared. Using the translation theorem, that should give me 2 over s plus 3 cubed. So we're getting closer here. So then using that to help us work with this one, and I'm going to pull the negative 1/4 out, but I'm still missing a 2 up here. Okay? And then this s plus 3 helps me with the translation theorem. So what do we end up with? Well, we're going to end up with negative 1/8 because we need the 2, so I'd have to multiply this by 2 over 2, pull this 2 in, leave this 2 out. And then we're going to get e to the negative 3t t squared. So this will be negative 1/8 e to the negative 3t times t squared. So that whole thing is my inverse Laplace transform. The hardest part about this problem was probably doing that partial fraction decomposition, which sometimes can take a really long time. All right, let's look at one more. Same deal. If I could do the inverse Laplace transform of 3s over s cubed times s squared plus 4 minus 2 over s squared times s squared plus 4, that would be nice. But does that really help? Okay, splitting apart the numerator. No, because of what the denominator looks like. If the denominator was just s squared, yeah, or if it was just s squared plus 4, yeah. So splitting apart the numerator isn't helpful. So instead, we're going to split apart the denominator. So let's go more partial fraction decomposition here. So I got s cubed times s squared plus 4. So one denominator could be s, another denominator could be s squared, another denominator could be s cubed. And then finally, another denominator would be s squared plus 4. Now when we do just s, since that's a linear factor, the numerator would be a1. S squared, a2, s cubed, a3. Yes, this is quadratic and this is cubic, but the factor itself, which is just s, is linear. So we still keep the numerators to be constants. This one's a different story. You got to remember what happens with quadratic denominators. Quadratic denominators, we got to change the numerator, not from a constant, but to a linear plus a constant. So bs plus c. Now, before we do all this work, remember, this is what we're going to have to take the inverse Laplace transform of. Is that going to be doable? And if not, then this method's probably not a good thing to continue down. But it will, right? Because if a1 over s, a1 being a constant, is what we need to take the inverse Laplace transform, that should be easy. We really just did it in the last example. Same thing for this one, same thing for this one. Now this one's going to take a little bit more work, but if you think about it, I could split this numerator part to bs over s squared plus 4. That'll be a cosine, and c over s squared plus 4, and that could be a sine. So this will be doable once we get through all this work. So get rid of the fractions. I get 3s minus 2 equals a sub 1 times s squared plus 4 plus a sub 2 times s squared plus 4 plus a sub 3 times s squared plus 4 plus bs plus c times s cubed. We can get started again with sort of our linear method. We can let s equal 0, but that's pretty much all that's going to work. But still, we might as well try it. So if we let s equal 0, this side will become negative 2. The right-hand side will zero out all the s's, leaving me really just with a3 times 4. So you see that a3 is going to equal negative a half. All right. That's the most we're going to be able to get done with that. After that, there's really not much else we can do by choosing certain s values. So I'm going to now multiply this side out again. Okay, not nearly as bad as the last one was. So here, this first one's going to give me a1 s to the 4th plus 4 a1 s squared. This one's going to give me a2 s cubed plus 4a2s. This one's going to give me a3s squared plus 4a3. And this one's going to give me bs to the fourth plus cs cubed. And I organized it this way because now my s to the fourths, s cubes, s squareds, s's, they're all grouped together. So thinking about if I put these together here, a1 plus b s to the fourth. This coefficient has to make this s to the fourth go away because there is no s to the fourth on the other side, telling me that has to equal 0. Same deal here. There's no s cubed on this other side over here. So a2 plus c has to equal 0 because that's my s cubed. Then I have the 4a1 plus a3 s squared. Again, that's got to equal 0 because there's no s squared on the left-hand side. I got 4a2s. That 4a2 has to equal 3 because of this over here in front of the s. And the last one, plus 4a3, that's the constant. That has to equal -2. Okay? Well, 4a3 has to equal -2. We already did that here. Right? That's going to give us -1/2. Let's go to this next one here. 4a2 has to equal 3, so it tells me a2 has to equal 3/4. That's good. That's some information we didn't know what a2 equals. This one is a1 and a3. We already know what a3 is, being -1/2, so this tells me that 4a1 plus -1/2 has to equal 0. All right, so that's going to give me that a1 equals, what, 1/8? All right, working our way down. This one, we know a2, which is 3/4, plus c has to equal 0, so c equals -3/4. So we're good there. And finally, a1, which is 1/8, plus b has to equal 0, so b equals -1/8. So this one wasn't nearly as bad as the last one, right? So we still now have to do the inverse Laplace transform, but at least we were able to get our a1, 2, 3, b, and c fairly quickly. Okay, so now it's time for those inverse Laplace transforms. Again, this one shouldn't be a big deal. Pull the 1/8 out, and now you're just doing the inverse Laplace transform 1 over s, which is 1. Next one, pull the 3/4 out. Inverse Laplace transform of 1 over s squared is t. Next one, pull the -1/2 out. Now we're missing a 2 up here because we really should have 2 over s cubed for our t to the second. So I'm going to need to have an extra 1/2, and I'll have t to the second. And then this one we're going to split apart. We're going to do this one, which we could pull the -1/8 out and have s over s squared plus 4. That'll be our cosine of, what is it going to be, 2t? And then the last one, which will be this one, pull the -3/4 out. We're missing a 2 up here in the numerator, so then I'll put an extra 1/2 here, and I'll have sine of 2t. So simplify some of this, and we're good. So we get 1/8 plus 3/4 t minus 1/4 t squared minus 1/8 cosine 2t minus 3/8 sine 2t. And then there's our inverse Laplace transform. And so now at this point, when you know how to do inverse Laplace transforms, you also know how to do Laplace transforms. And hopefully we're getting better and better and better at that. We can then look at using that to solve a differential equation. So that's the next step. But first we need more practice with this. So do the homework, start working on this so you get a little bit quicker with it, and then we'll start using it to solve our differential equations. Yes, we will use this to do something.